So we kind of jumped around a little bit. So I went back yesterday and looked at what we haven't covered yet. So we'll basically be finishing up with electricity and magnetism today. Then we'll go back to chapter 10, which is to do with temperature, heat transfer. That's chapter 11, I think. 12. 12's thermodynamics, which I could spend the whole semester on, but we don't have time, so we won't spend a whole lot of time. Then we'll go to 13, which is waves, 14, which is sound, and then last thing we'll do is optics, which is like telescopes and glasses and lenses and mirrors. So we got a lot to cover. So what this is out of the textbook, I think out of the algebra-based textbook, and it's a drawing of a AC generator. And that thing that I'll probably demonstrate it to you next Wednesday, and not next Wednesday, the Wednesday after next in class. But that little electric motor that I had, you can, instead of hooking up the batteries to the terminals, if you hook up a voltmeter to the terminals, you'll be able to see how it works as a generator. Okay, so this looks kind of like when we had the motor, right? The motor, an electric motor, you run current through a loop, and the current in the loop interacts with the magnetic field due to the magnets, and that causes you get a torque on the loop. And then when we get halfway through the cycle, we flip the switch, not really, figuratively, but we literally, that's not even right either. It gets flipped because of the way there was that little groove in the shaft, and it changes the current direction. So then the torque switches, or the current direction switches, which changes the force direction. And by doing that, we can continually make it rotate in one direction. So that's how a motor works. So in this case, what we have is we're generating electricity, and we're using Faraday's law that says that if you have a loop of wire, which has of a conductor, which has electrons that can move, and you move that loop in the presence of a magnetic field, you generate a current. The current direction is going to be based upon Lenz's law. Remember, we did that in lab the week before last week. And so that what we did was, when we did that with the moving magnet inside the coil, and we measured the voltage, and it went bloop like that, went bloop like that. So we were measuring the voltage for that particular thing happening. Here you have to have some way of transferring the current from the moving part to the stationary part, which is your power supply, your power. So you've got two rings here, one which goes, so you have a wire that goes to this ring, which is then connected. So this is stationary and this is rotating. So this thing's rotating, which is connected to the coil. And as the coil rotates inside that magnetic field, it creates a current which goes this direction. Okay, so as long as you have a complete circuit, like we learned we need to do on our Arduino, it doesn't work if you don't have your wires connected correctly. Now, if you measured the voltage coming out of this configuration, hold on just a second. I don't know why it does that. I can still hear it, even though supposedly the speaker's off. But anyway, so if I were to draw a plot of voltage or current as a function of time through that light bulb, what I would see is this. So as the loop is rotating, as it rotates in a clockwise fashion during this part of the rotation, you're going to get current flowing in one direction, but then the current direction changes and it goes the other direction. So this is an AC generator. It generates an alternating current. And that's basically what you're doing when you have a power plant, is you have some way of rotating in this case, a large amount of copper wire inside a rotating, what you would call the armature, and you've got some kind of way of creating a magnetic field, which may not be a permanent magnet, but may be actually an electromagnet. And that thing rotates around, and it rotates at a speed such that you get 60 hertz. So the turbines that spin in a power plant are turning at a very specific speed, probably 3,600 RPM, something like that. So you get 3,600 RPM would give you 60. So that's going to be what? 3,600 divided by 60. That's going to be 60 cycles per second, or 60 hertz. Yeah. So it's I guess it could probably rotate at 7,200 RPM, but I think usually they rotate at 3,600 RPM. And that's how you get. So in Europe, where they're using 50 hertz, they're probably rotating at 3,000 RPM instead of 3,600 RPM.
Question.
Yep.
Why is hertz measured with someone's name if it's not necessarily a unit?
Yeah, I mean, well, it is a unit. The hertz is the actual units for hertz is 1 over seconds. And the numerator is 1. Really, it's cycles per second. But cycle is not a thing. It's just a complete whatever. So it's inverse seconds. So it's, instead of saying 3,600 inverse seconds or 1 over second, it's just easier to give it a name. Yeah.
Yeah, because like a TV, it'll measure in hertz, and the turbine has hertz, but those, you can't do anything with those.
Yeah, I mean, on a TV, you're talking about how fast the wave is oscillating, whereas with a generator, you're talking about how many cycles that rotate. Yeah. So, the generator is going to go through one complete cycle in terms of rotation as it goes from here to here, and then it'll start over again. Now, if you have a different kind of attachment, this is what the DC motor uses. It had a copper ring, but it had these little slits in them, or in their case, it was a little, what do you call that, slot or something. And the little slot made it so that this half was not connected electrically to this half. But it's still rotating, and what happens is it basically changes the direction. Instead of the current going like this, or the voltage going like this, it switches the voltage so it goes this way. So it's always positive. Now, it's not constant, but you could put a capacitor on there, and the capacitor, take the output from this, and the light bulbs would still work, but if you wanted an actual constant voltage, you would use a capacitor to store the energy, and then you would feed the energy out from the capacitor instead of directly from the motor. So the key thing is that this is the electromotive force is always positive, even though it's not constant. But you can make it constant. If you average this out, you're going to average it out to some positive value. If you actually average this out, you're going to average out to 0. So, okay, so that's how motors work. Okay, these are to remind me to do things. So on the other day, we were talking about this LRC circuit. So we had a resistor, we had a capacitor, we had an inductor, and we had some kind of voltage source that was oscillating. Now, during this whole process, what happens is when we charge up the capacitor, so we put positive charge on one side and an equal amount of charge, negative charge on the other side, we're storing energy here. And you can kind of think of it like a spring. You know, if you have a spring like this, so this is not an inductor, it's a spring, okay? And you push on the spring, you compress the spring and it stores energy. And then when you let go of the spring, it releases energy. And it's doing that, it's storing that energy due to the electrostatic forces between the electrons. The electrons are getting pushed closer together, and so they're resisting because they're both negative charge, and so it pushes back. And then once you let go, then that energy is released as the molecules get a little bit further away from each other. It's kind of the same thing with the capacitor. What we're doing there is we're pushing all those negative charges on one plate. So it's kind of like a spring, except we're doing it with individual charges. So let me explain what I mean by that. So if you looked at the plate of the capacitor, here's the capacitor. Normally you've got an equal amount of positive and negative charges in there, but you take these negative charges. So let's make some negative charges up here, and we're forcing them into this plate. And what they'll do is they'll put themselves equally spaced along the surface. They want to get as far away as possible. If you remember the Van de Graaff generator, you know, all the positive charges went to the outside because they're trying to push away as far as they can. So when you try to force these negatively charged electrons into this conductor, it's like pushing against a spring. You're storing energy in here, and you're doing the same thing on the other side. You've got those positive charges that are wanting to push away from each other. So it is an energy storage device. As you use the battery to make that capacitor become charged, you're storing energy, and again, it's electrostatic energy because you've got electrostatic forces between the charges that want to get away from each other. They want to, just like a spring wants to uncompress. Also, when you have this inductor, what happens here is you have a magnetic field that's occurring. So you create this magnetic field around the inside the conductor, around the inductor. And what we're doing here is we're also storing energy. So we're storing energy in the magnetic field. So here we're storing energy in the electric field. And in the inductor, we're storing energy in the magnetic field.
Is there any energy loss associated with that, or do you just measure that as resistance?
Yeah, in creating the magnetic field, there's no energy lost. It's kind of like when we did the collision of the two carts that use the magnets. You know, remember the kinetic energy stayed constant. So when you use a magnetic force or field, you're not losing energy. You dissipate energy as the electrons have to flow through the coil. But if the coil had zero resistance, then there would be no energy lost. And my headphones are dinging, which means that I need to charge them up. But unfortunately, I left my cable in my office, so I'm going to run over there and get that. So just hold on here. We'll take a pause. Resume. Okay, so anyway, both of these are energy storing devices. In their ideal case, they don't dissipate any energy. They only store energy. So what would happen if I push the wrong button? Oh, where's my cursor? Lost my cursor. Oh, there it is. Just wasn't doing anything. So let's say I had just an ideal inductor and I had a switch and I had a ideal capacitor. And what I'm going to do is I'm going to charge the capacitor up. So let's say we put positive charges here So I'm somehow externally I'm charging up the capacitor, but because I don't have a circuit, nothing's happening because the switch is not closed. Now, when I close the switch, the inductor is basically a wire without any resistance. So if I just had a wire here, this thing would just go, it would go, it would discharge almost instantaneously. But because of the inductor and the corresponding induced voltage across the inductor, what happens is that it doesn't happen immediately. But at some point, this charge will move around the circuit. But as it's doing that, as the charge is moving from here through there, it's creating a magnetic field inside the inductor. But then once this thing is uncharged, the magnetic field in the inductor will then discharge, it will change, and that change will cause current. That magnetic field changing in the inductor will induce a current in the wire, which will then cause the capacitor to charge in the opposite direction. So first it discharges, stores the energy in the magnetic field. So you're losing the energy in the electric field as you discharge the capacitor. But as you do that, you're creating a magnetic field within the coil. So you're not losing the energy, you're just taking the energy from here in terms of an electric field into a magnetic field. And then as this is changing, that creates a current which then causes it to go all the way over here. Okay, so
When you first close the switch, it discharges the capacitor, stores the energy in the magnetic field.
yeah, not immediately though, it'll do it slowly. Well, not slowly, but it'll do it depending. And then recharge the capacitor, right. So basically what you would see if you plotted current in this circuit as a function of time, it would look something like, so the current's initially 0. You close the switch and the current goes like this. It reaches some maximum value in this direction. Then it actually goes back to 0 current. And I'll point out where these things correspond to the various storages. Okay, so here we'll say cap charged. Okay, so that's where the capacitor is charged. Now, when you get to a maximum current here, that is actually where the current goes to 0. The let's see which way that is. That's yeah. The capacitor's charged here, but in the opposite direction. Okay, so that says cap. They both say cap charge, but I'll say this is plus and this is minus. So here we start off with all the positive charge on this plate. Halfway through the cycle, this becomes positively charged. So it's the energy's still there. It's just in the opposite direction in terms of where the direction of the electric field, but it doesn't really matter as far as energy. So this, as a consequence, this point and this point are where you have the maximum magnetic field is in the in-between. And the same with here, but it's, again, you're going to go, when it's going this way, you're going to have the magnetic field going one direction, maybe, I don't know which way it is, when this thing goes and charges back up and then comes back again, so then it'll go the other way. It'll just oscillate forever. So the inductor, and it's like, analogies, we were talking about analogies the other day. If you have a spring, and I'll put it sideways so we're talking about a spring out in space, so there's no gravity. And if I take the spring and I have some mass on the end of it and I compress it, what will happen is this mass will will accelerate to its maximum value, and then it'll go out here and it'll get stretched, and it'll have the maximum stretch, and it'll keep oscillating back and forth. As long as there's no energy lost due to friction, this thing would just keep oscillating forever. This is this energy is due to the energy stored in the spring, and this energy associated with the mass is the kinetic energy. So what we do is we alternate the energy between kinetic energy and spring potential energy. What we have in this electric circuit is we go from electric and energy stored in an electric field to energy stored in a magnetic field, because when this is uncharged, there's no. So when you have this maximum magnetic field, this will be uncharged. It'll be the same amount of charge on either side, so there'll be no electric field here, and all of the energy will be stored in the magnetic field. Same with a spring mass system. Okay. So I think we talked about this back in when we were talking about capacitors, but the energy stored in the electric field in a capacitor is equal to 1/2 the capacitance times the velocity squared. I mean, not velocity, the voltage squared. Remember that video with the big capacitors? He did some calculations looking at how much energy was stored in the capacitors based on the voltage and the capacitance of the capacitor. So that was where we saw that. And it looks very similar to if you look at the energy in a spring. The energy stored in a spring is equal to 1/2 kx squared. So the analogous property for springs and capacitors is the capacitance and the spring constant. The thing that we're displacing here is actual physical displacement here. We're talking about voltage, which is kind of remember that's potential energy per unit charge. Okay, so that's the energy stored in an electric field. And for a magnetic field, that's what I was trying to get to, the energy stored in a magnetic field is equal to 1/2 the inductance of the inductor times the current squared. So again, it has the same 1/2 some constant times some variable squared. In this case, it's current squared. So if we go back to our picture here, the maximum current is here, so the maximum magnetic field occurs here. There's no energy in the capacitor at this point. Here there's no energy because the current's zero, there's no energy in the magnetic field. Here we have the maximum in the magnetic field and zero in the electric field. Here we have the maximum in the electric field but zero in the magnetic field, and it just switches back and forth. Okay, I'm going to come back to that in a second. Actually, I'm not, because I didn't write it down, but I have one more thing to do here. So this is back to our experiment that we did in class, our computer experiment. So if you have a resistor and you have a capacitor and you have an inductor, so this has some resistance value, this has some capacitance, this has some inductance, and you oscillate this thing, there's going to be some relationship between, remember the relationship between the maximum voltage and the maximum current was the impedance. And the impedance was a function of it was the resistive reactance plus the difference between the inductive reactance and the capacitive reactance squared. So where this is a minimum, where the impedance is a minimum, is where this is equal to that, because this goes to zero. The capacitor and the inductor's effects cancel each other out because they're 180 degrees apart. So when one goes up, the other one goes down the same level, and they cancel out when you add them together. So that when this is a minimum, that means that it's kind of like resistance. It's the resistance of a circuit that includes all three of these the resistance to how much something can oscillate. So when this impedance is a minimum, you get the most voltage for a given current. Okay, so, and that has a special name. It's called resonance. So I don't think, is it RAE? Maybe that resonance? Resonance? Resonance. I guess it's just resonance. Okay. So resonance occurs when the inductive reactance equals the capacitive reactance. And remember, the inductive reactance was equal to 2 pi times the frequency times the inductance, and the capacitive reactance was 2 pi times the frequency times the capacitance. So the question is, at what frequency do we have resonance? So all we have to do is cross multiply, so we get 4 pi squared f squared L times C equals 1. So all I've done is taken this and multiplied it by that. So you get 2 times 2, which is 4, pi times pi, f times f, and L times C. So if I then divide by 4 pi squared LC, 4 pi LC, and then take the square root, I'll get that the resonance frequency is equal to 1 over, this was 2 pi squared. So when I take the square root, I'll get 2 pi times the square root of L times C. So that's the way you figure out what is the resonant frequency for an LRC circuit. You just take 1 over 2 pi times L times C. The other day what we were looking at, we had an inductance of something like 0.01 henries. I'm just making this up. It's around this value. And let's say we had 2 times 10 to the minus 6 farads. So using those two values, which are kind of typical, my calculator. So let's put those in. We'll get the resonant frequency is 1 over 2 pi times the square root of 0.01 times 2 times 10 to the minus 6. One divided by 2 divided by pi divided by the square root 0.01 times 2 e to the minus 6, and I get 1,125 hertz. Okay. So what that means is at frequencies less than that, the capacitance is going to start to dominate as you go to lower and lower frequencies. The capacitor is the thing that limits the amount of current that alternating current that you can get through your circuit. At frequencies greater than 1125 hertz, then the inductor starts to be the limiting factor, because as you oscillate more quickly, the slope or the rate of change in current is greater, and so the inductor is more of a thing that's kind of limiting it. But this particular frequency here is the one that will give you the maximum output. So I made this, I did this yesterday. I was trying to learn how to use MATLAB. So I thought I could use it to demonstrate this. So I did. Okay, so I'm going to show you the program I wrote. Computer programming. So it's here. It's called a Bode plot. And this is basically what we were doing the other day in when we use that software to look at the graphs, but this is just how those were generated. And I'm going to put it into a Word document so we can see see this a little easier. Okay. Well, didn't like that. Edit, copy. Okay. Paste. There we go. Okay, so now we'll zoom in so you can see it better. And I included some comments, so there's a lot of comments. So the first line says the resistance is some value. R is equal to 20 ohms. The second one is the inductance, which is 0.001 henries. The third number is capacitance, is 2 times 10 to the minus 6. The next command, what I'm doing is I'm creating a range of frequencies. And I did this because I found it in a book. I have a book on electrical engineering, and they said, here's a MATLAB program. I'm like, oh, that's cool. So I modified it. So what this means, it says start at 1, increment in increments of 0.01 to 5. So this creates an array which has 500 elements. So it has 1, 1.01, 1.02, 1.03, all the way up to 5. So this is the starting number, this is the ending number, this is the increment. So I've got 500 numbers. Those are my frequencies. And if I go back to here, you can see that in calculating my impedance, the impedance, remember, is the inductive impedance is a function of frequency and the inductance. And the same thing for capacitors. So that's why I'm generating a lot of data for different frequencies. Okay, the next thing is this says take this number and make it the power of 10. So I'll start off with 10 to the first power. So I'm going to start off with frequency of 10 hertz. So this is now converting those equally incremented values into not logarithmically incremented. So it starts off at 10 to the first power using this value. 10 to the first power is 10. And it goes all the way up to 10 to the fifth power, which is 100,000. So it's a way of generating frequencies between 10 and 100,000, but not equally incremented, but logarithmically integrated. Okay. W is basically 2 pi f, which is W is, they're saying that's omega. That's the frequency. This would be what we would call the what would we call that? Angular frequency. This is the frequency in hertz. This is the frequency in radians per second. And then you can calculate the X sub L is the inductive reactance, which is 2 pi f times L. And this is the capacitive reactance, which is 1 over 2 pi c. So that's just using the definitions. And then Z is equal to the square root of R squared plus X sub L minus X sub C squared.
So for that, if X of L and X of C are the same size, and you simplify that, wouldn't that mean that the impedance is equal to the resistance just at the point where those two things are equal?
Yeah, what I'm doing here is I'm going to plot the impedance for a lot of different frequencies, and we'll see that when these equal to each other, that we'll have a minimum for impedance. So I'm showing you not just the point where it's minimum, but how it gets to that minimum. And the key thing too here is that makes this MATLAB interesting is you'll notice this little dot. So I have dot power. I have, in this case, I'm just multiplying 2 pi times, because these are all arrays. So there's 500 values here, and there's 500 of these. And so when I do these multiplications, I do 2 pi f, not just times, but I do dot times. And what that means is that I multiply every element in this this matrix by the single impedance value. There's only one impedance. There's only one inductance value. And then I also take every value in this W matrix and I divide it by the capacitance. So these are matrices, and you've got to use these special commands when you do matrix commands instead of just. Likewise here, R is a matrix, so instead of squaring R, I square it with this little dot, which means I'm taking every element of that matrix and squaring it, not squaring the actual matrix. I'm not multiplying the matrix by itself. I'm squaring everything that's in there. And then this function tells me to do a semi-log plot where I'm plotting frequency on the x-axis, and I'm going to take this number z, I'm going to take the log to the base 10 and multiply it by 20. So it's kind of like doing decibels. It's just a different way of presenting it. Okay, so that's it. That's the program. If I go to my command window and I write in Bode underscore plot, got to use capital P, and I say return, it generates that graph. Okay, and it's kind of like the graph that we looked at using that LT Spice, except it's probably a larger frequency range. And what you find out is that the minimum impedance occurs at a frequency of around, this is 1,000, this is 2,000, 3,000, so it's about 3,500 hertz. Okay, and if I change the value of the capacitance or the inductance, it would change this point. And so let's given the values that I used in this problem, let's figure out using that formula what the resonant frequency is. Show you that it's the same thing. So I think the only thing that's different is that this was 0.001. So let me fix that. I think I had two. Let's go back to my thing here. So I had 2 times 10 to the minus 6 and 0.001. Okay, so using those new numbers, I'll get 1 divided by 2 divided by pi divided by the square root of 0.001 times 2e to the minus 6 power, and I get 3,560. So it tells me that my resonance frequency should be 3,560 based on that data, and my plot here shows that the minimum impedance is about 3,560. You can't read it to that exactness. And if you go either side of that frequency, the impedance becomes larger. Impedance is like resistance. It's going to make it so that for a given level of current, that the voltage is going to be a lot lower because of that. Okay, anyway, that's... Okay, now we're going to talk about transformers. We talked about these briefly before, but I usually put a transformer problem on the test. So the whole idea behind a transformer is you have 2 coils of wire with different number of loops. So I'll make this one more loops. Okay. So this has N1 loops and this has N2 loops. You also usually have an iron core that goes like this. And we saw the other day that when you stick that iron core in there, it enhances the magnetic field inside the coil. And by connecting this, you can basically connect these 2 magnetic fields by using this core, and the magnetic field will go right around this core if it's made out of the right material, out of the proper kind of iron. So that's a normal transformer. And what's happening is you are creating a magnetic field in the primary loop. We'll call this the primary. So we're going to vary the current through the current and voltage through the primary loop. And what that's going to do is it's going to the changing current is going to create a changing magnetic field inside the core, and that changing magnetic field is going to come over here and then go through this secondary loop. So the secondary loop is going to see the changing magnetic field that the primary loop causes, and because the magnetic field strength is the same all the way around this loop, you have the same changing magnetic field, but you have more loops. So Faraday's law says that the electromotive force is equal to negative N times d phi dt. So if we have the same d phi dt and you change the number of loops, you're going to change the voltage. So the way I've got it right now, since N2 is greater than N1, the voltage in the secondary loop, and we'll use RMS because it's always has to be an alternating current. VRMS 2 is going to be greater than VRMS 1. So the voltage, just think of it as voltage. You're going to have, by increasing the number of loops, you're going to increase the voltage in the secondary loop. Now, but you can say, but if N2 is less than N1, then you have voltage decreases. This would be called a step-up transformer because you're increasing the voltage. Here, the second case, the RMS voltage of the secondary loop is going to be less than the RMS voltage of the primary loop, and we call that a step-down transformer. And it turns out that the ratio of the number of loops is equal to the ratio of the voltage in an ideal transformer. Okay. So you can see that if I solve for the T2 stands for secondary. So what you'd get is that the secondary voltage is equal to the primary voltage times N2 over N1. So if N2 is greater than N1, this is a number greater than 1, and therefore your voltage in the secondary loop is greater than the primary. If N2 is less than N1, then this number is going to be a number between 0 and 1, so your secondary voltage is going to be less than your primary voltage. And that's all there is. It's just a simple equation. But there's also a question of how much current are you going to generate in the different loops. It turns out you don't have the same current in each loop. And the way in an ideal transformer, the power in the primary loop equals the primary in the secondary loop. So what we say is that the RMS voltage in the primary loop times the current, RMS current in the primary loop, is equal to the RMS voltage in the second loop times the RMS root mean square current in the secondary loop. So if you increase the voltage through the transformer, you have less current in the secondary loop. If you decrease the voltage, then you increase the current. So they go opposite of each other. So let's just do an example here. So here's my problem. This would be a problem like you'd have on the test. So we have a transformer. Whose primary side has 50 loops and a secondary side that has 300 loops. If the primary voltage is 5 volts RMS, what is the voltage in the secondary loop? Okay, so all we have to do is just say V2 equals V1 times N2 over N1. So our voltage is 5 volts RMS. Our number of loops in the secondary is 300. The number of loops in the primary is 50. So 300 divided by 50 is 6, so you get 30 volts. So that's your secondary voltage. Now from a current standpoint, you've got V2 I2 equals V1 I1. So the current in the secondary loop is going to be equal to the current in the primary loop times V1 over V2. So if so, let's say so the next part of the question is if the current in the primary loop is, let's say, 0.07 amps, what is the current in the secondary loop? Question mark. Okay, so all you do is you take 0.07 amps. Voltage in the primary loop is 5 volts. The voltage in the secondary loop is 30 volts. So you take 0.07 and basically divide by 6. And you get I2 is 0.012 amps. So you can see the voltage goes up, but the amps go down. I think if you look on the transformer here, let me pull out my transformer. Whoops, got too many things connected here. I don't have my glasses to read this thing. Yeah, it's too small. But there's probably something on there that talks about amps. So that's pretty much it with the transformers, except one thing I thought about yesterday, and I didn't bring it with me. But you know those iPhone chargers? You know, let me disconnect here for a second. Well, you know those transformers we use in the lab for the interfaces. Those things weigh a ton. They're like this big, and they weigh a ton because they have iron inside that are used to deal with a standard kind of transformer. They call these linear transformers. So the primary side is at 60 hertz. The secondary side is at 60 hertz. And we did that experiment in class where we varied the frequency of the signal, and we saw that, you know, as you lowered the frequency, that the output voltage wasn't quite as good. But, you know, we said it's sufficient for this thing to work. And we don't need any fancy electronics. All we need is a line coming in with a coil, a metal core, a secondary coil that, in the case of these step-down transformers, you'd have more in the primary loop and less turns in the secondary loop. But you know, this one weighs, it doesn't weigh as much as that old transformer. But it does weigh something. You know, it does have some weight. So you can imagine there might be some iron in there in the standard transformer. So the question I asked myself, why are those iPhone chargers so small? You know, we're still charging up our phone. It's still power coming from the wall. It comes out into a USB. It's, I don't know how many volts, but and then it feeds that into our phone. You're probably not going to put a transformer in your phone because it's going to weigh a lot. So you're trying to minimize. So you do have the extra weight that you have from a transformer, but again, it's so darn small. So I didn't know this till yesterday, but it's interesting. So here's the answer. Anybody have any answer? How do they make those things so small? Well, it turns out that the frequency of the oscillation of the signal that causes the transformer to work influences how much iron you need for the transformer to efficiently work efficiently. So, you know, these transformers, besides being heavy, need a lot of iron. They also get kind of warm as well. You know, you're losing energy inside this. So it turns out that if you increase the frequency of the oscillation, then you need a lot less material to make for your core to connect the two coils together. So I'll write that down. So to use less iron core, you need to increase the frequency of the oscillation. So what we need to go is go from 60 hertz to something higher. So there's two questions. How high do you go, and how do you get to a higher frequency? You know, say we want to go to 100,000 hertz. How the heck do you go to 100? How do you get an oscillating signal at 100,000 hertz? It turns out that, yeah, that's what they do. So here's the explanation without going to the hour details that I watched yesterday. I didn't watch it. I kind of skimmed through. So what they do is they come in. You've got this alternating signal, 60 hertz. Then you convert that into a DC signal. And the way you do that is you use a rectifier, use the diodes. There's this thing called a, what's it called? Anyway, it's four rectifiers together, not four rectifiers, four diodes. So you take four of those little diodes that we played with in the lab. We use that to protect our motor. And you can basically come out with a DC signal. It's not flat, but it's all positive. So you can make it so it's always positive, and then you put a capacitor in there to smooth out the wrinkles, like Euro Specialties in Roanoke, smooths out the wrinkles in the signal. So you end up with a DC source. That doesn't take too much electronics and not too fancy. Okay, then what you do is you take that DC signal and you use a transistor in conjunction with an oscillator to then create this oscillating signal, which has a very quick oscillation. So it goes between 0 and whatever this DC signal is, about 100,000 times per second. So that signal is then, that is the alternating signal that goes into the cores, and that transforms it to the secondary loop to change the voltage, which is again dependent upon the number of loops. But because the oscillations are so quickly, because d phi dt is huge, you know, the rate of change in the magnetic field is huge because it's happening so quickly. It's like me going, you know, just trying to move my hand faster and faster. So we're going from moving at 60 times per second to 100,000 times per second. And that process makes it so that you need a much smaller core to transfer the magnetic field between the two coils. So I thought it was pretty cool. And they use that not just in chargers, not just cell phone chargers. I wondered whether even this one might have something like that in there. It's just not quite. The other issue, why they said you should buy, this is somebody who probably works for Apple, why you should buy the Apple chargers instead of the cheap knockoff chargers. So the reason is because the high frequency oscillations in the charger create radio waves, which can then interfere with your cell phone's working. Okay, so what they do is they use some higher quality components that the cheaper guys wouldn't, and they also use some shielding to shield the charger from the phone so that those high frequency signals don't propagate.
Just get a longer cord.
So yeah, that was it. You can get a longer cord, or just don't use your cell phone while you're charging it. It doesn't really matter. So anyway, that's yeah, that's the bottom line. Because somebody else said, "Oh, that's a bunch of baloney. That guy doesn't always talk."
Did he tell you that before or after he found out you were an engineer?
No, it was just some article.
Oh, okay.
So it was just somebody who wrote. Is somebody who wrote why? I think I looked up why. How does a Apple cell phone charger work? And so that was the question I asked. Let me see if I can find the actual article. How does an iPhone charger work? Question mark. Okay, so that's what I asked. And there we go. So why is Apple's iPhone charger a high-tech work of art? So there's your Apple phone charger.
I was washing my sheets and my charger got warmed up in the sheets and I put it in the washing machine so now it doesn't work.
So this is what the inside of the Apple it looks like. You can see we have these two big capacitors. So those are used for smoothing out the signal. You've got two boards that are the different sides of the different voltages. Yeah, they use 70,000 times per second, so 70,000 hertz. And it comes with super strong AC prongs and complex over temperature, over voltage shutdown circuits. Then you got these guys' comments. What did they say? Says, that's just a charger for God's sake. There's no rocket science involved or state-of-the-art tech. It's pretty much the same size, blah, blah, blah. So, yeah, it's interesting hearing people's comments about the whole thing. But anyway, that's how it works. Yeah.
Some chargers will actually work with your phone. Like Samsung has special fast charging cables that actually, it's called adaptive fast charging, and it will adapt to what your phone can handle without destroying the battery. So like old phones won't charge as fast, but newer phones, it will actually up
Oh well,
sending out.
yeah. Just it limits the charging to its maximum before it overheats or something like that, right? Yeah. So this whole idea of when the power is produced at the power plant, it's produced at, I don't know, maybe like 3,000 volts, something like that. So what they do is they increase the voltage for transmitting the power from the power plant to the local area, and then they have substations which then convert that from hundreds of thousands of volts to tens of thousands of volts. And then locally you'll see that sent to then you'll see the transformers that are on the telephone poles or the poles, and those will reduce them down from 10,000 volts down to your house voltage. So they go through these different voltage levels for safety. You don't want to have 100,000 volts that you could run a truck into easily. So the high voltage transmission lines are high above the ground and safe. So the question is, why do they use such a high voltage? And that's one of the reasons they ended up without AC power, was because you could transmit the power or transport the power from one location to the other with much less resistive loss, because you've got cables. Here are your cables that are taking it from the power plant to us, Covington. And if you did it at 120 volts, you wouldn't get hardly any current through here at all. But as we were saying, the power dissipated is equal to I squared R. So if there's any way that you can decrease the amount of current through the power lines, then you're going to decrease the amount of power that's dissipated. So remember, power is also equal to voltage times current. So if I want to transmit a certain amount of power, I can do that if I increase my voltage. So if I increase the voltage, then I decrease the current. So by decreasing the current, then I can decrease this contribution to the power loss in the lines. And so that's why they do it. It's to increase the voltage so I can run lower current. Lower current is squared, so that ultimately is going to give me less power consumption in the line. And then, but ultimately I have to bring it down to a voltage that people can deal with safely. So you put the power lines locally are probably 10,000 volts, and then that is stepped down in a transformer down to 120 volts or something like that.
Did you see where the power plant exploded last night at the Bottock County?
I saw it. Well, the substation, yeah. So that's going from hundreds of thousands of volts down to 10,000 volts. Oh, do you? Yeah, I saw it this morning on there. Is this your video or just one that's on the news? Oh, you were there taking it? Okay. So how did it transpire?
I'm not exactly for sure.
I mean, how did you know to be there? Was it starting to do something and then?
I was herding cattle with my buddy on his ranch.
Okay.
Right there on Country Club Road, and we were looking down there over the hill, and we were like, "You hear that humming? Like you could obviously hear something." And as we're looking, he's like, "Well, my phone will pick it up," so he like zooms in on it or whatever. And as soon as that happens, you just see this giant arc just cross and just done, fried everything.
Yeah. Yeah. So they're going to be out power for.
Oh yeah, my house will probably be out of power for 10 days or so.
You think that long?
Oh yeah, because we're at the very end of the line, plus the down trees that are on the road. So
Oh, okay.
I was like literally rock crawling over trees to get here today.
Yeah. So we had to have class because Sean came. If you you wouldn't have been disappointed. Okay. So the last thing we're talking about here, we talked kind of in general about it, but there was this guy named James Clerk Maxwell, and he took a lot of different people's theories and put them together and came out with his Maxwell's, I don't know if they're really Maxwell's laws because he stole them from somebody else, but it kind of summarizes what we've done in the last 7-8 weeks. So let's just go through them. So one is electric field lines originate on positive charges and terminate on negative charges. So what that's saying is that, you have an electric field around positively charged particles and the electric field's pointing outwards. And if you have a negatively charged particle, you have an electric field around a negatively charged particle. Those are pointing inward. So if you put that, wherever we played that game, the electric field game, we took a positively charged particle, it was repelled by other positively charged particles, or it was pushed away from it in the direction of the field lines. And if it had a negatively charged particle, it would be drawn towards the negatively charged particle. Okay, so you do have sources of positive and negative charge, which are electrons and protons. Now, magnetic field lines, they don't have that same situation. They create loops. So even a magnet has a north and south pole, but if you looked at the magnetic field lines, they actually are continuous. When we looked at a wire, we said the magnetic field lines around a wire were concentric circles. So it didn't have a starting place or an ending place, which is different than electric field lines. We also found that a varying magnetic field induces a voltage or an EMF, and that voltage then creates an electric field as well. So that's Faraday's law. We've been using mostly the first part, that a varying magnetic field induces a voltage. But it's true that if it induces a voltage, it induces a current, which causes an electric field. Okay. And then magnetic fields are generated by moving charges or currents, which are moving charges that are inside a wire. That's Ampere's law. So what he did, he started with all those things. He came up with those laws. I showed you those fancy vector laws that were really confusing. And basically what he did was he said that the third, and I mentioned this early in the semester, but from this information you can come up with one additional thing, that accelerating charges create varying electric and magnetic fields, which consequently generate electromagnetic waves. So what electromagnetic waves are varying electric fields and magnetic fields that feed off of each other. So it's kind of like back when we were talking about this oscillator circuit, you know, we had way back here. So, you know, we had this discharge of the capacitor, which is storing energy in the electric field, then creates a current, a changing current, which creates a magnetic field and a changing magnetic field, and they kind of interact with each other. And here we have this oscillating nature. And the same thing could be said true about these electric fields and magnetic fields. Instead of in terms of capacitors and inductors, they just happen in space, which is kind of the cool thing. So these varying electric and magnetic fields feed off of each other, and that feeding off of each other allows that energy that are stored in the electric fields and magnetic fields to be propagated through a vacuum. So we have all kinds of different kinds of electromagnetic waves. Let's just look at those before we quit. I'll come back to this next time. But, you know, these are all the different kinds of electromagnetic waves. We'll start down here at the bottom end. So you've got things like radio waves, TV, microwaves, infrared, visible light, which is a really small section of the whole thing, ultraviolet, X-rays, and these are all a result of accelerating charges. So in a radio, for example, say a normal old-time radio, you had an antenna, and you would apply a voltage to the antenna, and it would cause electrons to go back and forth in the antenna, and those electrons moving this direction would create electric and magnetic fields, which would then propagate in space, and then you'd be over somewhere with your antenna for your receiver, and they would be able to sense that electromagnetic field that's traveled through space, and then you take that signal and then you amplify it and then you listen to it. Okay. Whereas for light, what's happening there is the electrons in the different energy levels of the electron structure of a molecule. That's where, so you have electrons moving between different energy levels, but it's still accelerating, and that jumping between the different energy levels in the molecule happen much more quickly than the electrons moving in an antenna, so they generate higher frequency and smaller wavelength electromagnetic waves, but they're all electromagnetic waves. So radio waves, microwaves, light all travel at the same speed, the speed of light, right? Okay, so we'll continue on this. So we're not quite finishing chapter 21 yet. We've still got some more.